Hi everyone, my name is Lorraine G. Agustin and I will be discussing my case study titled Bridge Temperature Analysis. Hi, I'm looking at an issue where our bridge steel's structure heats up and cools down throughout the day. I need to determine if these temperature changes could cause thermal expansion problems. If the bridge expands too much in the heat and contracts too much in the cold, it causes stress fractures or even structural failure over time. I can model this using Newton's law of cooling, a first-order differential equation. Here's the equation we use to model temperature changes. Wait, that formula looks similar to the one used in conduction for heat transfer, right? Well, in heat transfers, it involves multiple principles and mechanisms, but for now, let's focus on Newton's law of cooling. This equation describes how fast the bridge temperature changes over time. T represents temperature at time, Tm is the surrounding ambient temperature, which we assume is constant. And K is a positive constant that depends on the characteristics of the object. And dT over dt represents the rate of temperature change. So if it's really hot outside, the bridge's temperature rises quickly at first, but slows down as it approaches the ambient temperature. Similarly, at night, when it cools down, temperature drops quickly at first before stabilizing. This equation helps predict extreme temperature shifts and prevent material damage. Okay, let's consider an example. If the bridge starts at T of 0 is equals to 20 Celsius in the morning, but the air temperature rises to Tm is equals to 35 Celsius. How long before the bridge reaches 30 Celsius? The general solution to Newton's law of cooling is dT over dt is equals to negative K multiplied by T minus T of m. Substituting the values, I can calculate the time required. First, I need to determine the value of K. Based on common engineering estimates, steel bridges typically have a heat transfer coefficient that results in a temperature changes of about 3 to 5 Celsius every 10 minutes under normal conditions. If I assume a moderate heating environment with wind and sun exposure, a change from 20 Celsius degree to 28 Celsius degree in 10 minutes is reasonable. Using the assumption, I can calculate K. So 28 is equals to 35 negative minus 15 E raised to negative 10K. So 7 over 15 is equals to E raised to negative 10 over K. So we will take the anti-logarithm is equals to ln 7 over 15 is equals to negative 10K. Next, we will be having a ln 7 over 15 over negative 10 is equals to K. Then our K is equals to 0.0686. Taking the anti-logarithm, I solve for when T is equals to 30 Celsius degree to see how long it will take before the bridge reaches that temperature. This helps decide when to check for expansion stress. This was super helpful. Monitoring temperature shifts will allow us to set up an expansion joint inspection schedule to prevent damage. Thermal stress is no joke. A small crack today could turn into a major failure in a few years. Good thing we checked the math before that happened. Differential equations don't just live in books. They help keep our bridges safe.